We're going to be talking about thermodynamics in this chapter, and this is a little bit different than some of the other chapters we've talked about. We're going to get away from the stoichiometry, the multimass conversions, just a little bit different. I think some of you will find it a little bit easier. Please make sure you stay on top of all of your classwork. I didn't see that so much in the last chapter, which I think made it extra challenging for you. And this chapter will be a little more concise, not over spring break, and I think that will be beneficial as well. Thermodynamics, as defined, is the study of all energy changes that accompany physical and chemical processes. Physical processes, for example, such as melting, freezing, condensing, any type of phase change. Chemical processes, what you're talking about there is a chemical reaction in which substances react to form other ones that have different properties than what you started with. There's a little video that goes over some basic terms. I'll show that to you in a minute. There are 3 laws of thermodynamics. We're only going to hit the first. The first law of thermo we've actually talked about previously. Energy cannot be created nor destroyed in a chemical reaction. It's just converted from one form to another. So for example, if you had photosynthesis, and if we were to look at photosynthesis, you've seen this before in biology. Carbon dioxide and water react to form glucose and oxygen gas, and you can balance that equation very simply. The production of glucose from carbon dioxide and water requires energy from the sun. So you start with light energy and you convert it to a form of energy that the plant can utilize in the form of glucose. The reverse process is cellular respiration, which you also would have talked about. Oops. Hey, watch your mouth.
Don't be fresh.
That just makes it funnier. For example, if you look at cellular respiration, which is the reverse process, you know that energy is released in the form of ATP. And you've talked about that previously. Those of you heading back to AP Bio, you'll talk about it in far more detail. This will be an endothermic reaction in which energy is absorbed, an exothermic reaction in which energy is released, and we'll talk about that in a lot more detail. Now, there are 2 factors that determine whether a reaction occurs. The first is it thermodynamically favorable or spontaneous? Does the reaction occur without any assistance? Is product formation favored? That's what we're going to look at in this chapter. That's one criterion that must be met. A second is the reaction kinetically favorable? Kinetics is the study of reaction rates and the factors that affect them, and our next chapter will be on kinetics. For a reaction to occur, it must be both thermodynamically favorable and kinetically favorable. For example, diamond can be converted to graphite. This is a thermodynamically favorable reaction, and we'll show you how to determine whether reaction is thermodynamically favorable in this chapter. However, the reaction occurs so slowly that it's not kinetically favorable, and as a result, you don't get graphite from diamond, and why would you want to anyway? Graphite you use in pencils and things like that to make keys go into locks better. Diamonds, well, those are far more valuable and girls like them more. So why would you want to convert it? This is a reaction that we have run this year. We reacted silver nitrate. That's what I told you. Be careful that you didn't get on your hands, because if you went out in the sunlight, your hands would turn brown. If you react it with table salt in an aqueous form, you generate silver chloride, which is a white precipitate. And when we did our halide reactivity lab earlier in the year, you saw that most silver halides are precipitates. They're not soluble in water. And this is one of those exceptions. All chlorides are all chloride containing compounds are soluble in water, except those that contain silver, lead, and mercury. And this is an aqueous substance as well. So this reaction is both thermodynamically favorable and kinetically favorable. And we'll look at the thermodynamic favorability in this chapter. There are some basic terms that we want to define: energy, heat, temperature, and heat transfer. Energy, very simply, is the capacity to do work or transfer heat. Heat is transferred from a warm object to a cold object, and we'll talk about that. There are many, many, many different types of energy listed there. Thermal energy deals with heat energy, for example, from the sun. Kinetic energy deals with motion, and we'll take a look at that. Potential energy is the energy stored is the energy that, I can't get that word out. That wasn't the word I was saying. Potential energy is more correlated to position, all right? And we'll take a look at that in just a minute. The unit of energy is the joule. The joule is also a kilogram meter squared per second squared. We're not going to use that. 1 calorie, this is not a nutritional calorie, is 4.184 joules, and this differs from a nutritional calorie, and we'll talk about that. I'm going to flip to the video a little bit because he talks about this in a little bit more detail, not a lot, although all you need to know is here. The unit for energy in the international system is the joule, and that's what we're going to be dealing with. So let's take a look at that video.
Hey, what's up everybody? In this video we're going to talk about one of the most important and interesting, at least in my opinion, aspects of chemistry, and that is thermochemistry. So you can probably already make a pretty good attempt at guessing what thermochemistry is, owing to the fact that we have a picture of a power plant here on this slide. But let's actually go into the scientific definition of thermochemistry and see how far that takes us. So according to my chemistry textbook, the definition of thermochemistry is the study of the relationships between chemistry and energy. Okay, so now we're getting somewhere. So chemical reactions, some of them release energy, some of them require energy, some of them release a lot of energy, some of them release a little bit of energy. Some chemical reactions require a lot of energy to get going, some of them don't require much energy, and so on and so forth. So we're starting to get the idea of what thermochemistry is, but in order to understand this, we need to be able to define the word energy. Now, again, to define the word energy, I just kind of took another look in my chemistry textbook, and I found that energy is the capacity to do work. So it's kind of this cat and mouse game we're playing, where each new definition that we look at begs a question about the definition of another word. So with thermochemistry, now we have to define energy, and then with energy, the capacity to do work. Well, what the heck is work? So now we got to define work. And according to my chemistry text, once again, the definition of work is the result of a force acting through a distance. So again, energy. If something has energy, that means it has the capacity to exert a force on another object and move it through some distance. Okay, so now that we have just been inundated with vocabulary, it seems only fitting that we introduce a little bit more vocabulary, right? And so we're going to talk about some types of energy. The first type of energy that we're going to talk about is called potential energy. And the potential energy that an object has is associated with the object's position. Potential energy could also be associated with the composition of an object, so how that object is put together. And of course, we're going to elaborate on potential energy a little later in this playlist. So for instance, you see this little scientist over here, he's holding up an apple relatively high off of the ground. That apple, simply because of its position within Earth's gravitational field, has a lot of potential energy. And of course, if you release that apple, the apple would fall. And the reason why that's true is because scientists have determined that nature tends to proceed in a way that minimizes its potential energy. So whenever possible, nature is always going to try to do whatever it can to lower its potential energy and get it as low as possible. The second type of energy that we're going to discuss is called kinetic energy, and the kinetic energy of an object is associated with its motion. So something that is in motion has kinetic energy, something that is at rest has no kinetic energy. And finally, the third type of energy that we're going to talk about in this video, there are more types of energy, but for now we can just limit our discussion to 3. The third type is called thermal energy. So here's a nice photograph of the sun that I found. And as you've probably already figured out, thermal energy is associated with an object's temperature. And thermal energy is actually a type of kinetic energy because thermal energy originates from motion, just as regular old kinetic energy does. Thermal energy originates from the motion of particles. So you have atoms and molecules moving around. You may have some subatomic particles moving around really fast. All of those atomic, molecular, subatomic particle motions are what are the origin of thermal energy. So again, we have potential energy that's due to position or composition, kinetic energy that's due to motion, and then we have thermal energy which is associated with temperature. And remember, thermal energy is a type of kinetic energy. So the last thing we're going to do before we wrap this video up is talk about some of the most common units of energy. And there's a lot of units of energy out there, and we're going to talk about just a few here in this video. Now, the SI unit, remember SI stands for International System of Units. The international unit for energy is called the joule, and it has the symbol capital J. And the joule is a derived unit, so it comes from other SI units. And the definition of the joule is 1 kilogram times square meters divided by square seconds. Okay, now the joule is not a very large unit of energy. There's really not a lot of energy in a joule. And so oftentimes you're going to see energy recorded in kilojoules, where of course 1 kilojoule is equal to 1,000 joules. Now another common unit of energy is the calorie, which I'm sure you are familiar with, and that has the symbol lowercase cal. And the definition of the calorie is the amount of energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. And if you wanted to convert between calories and joules, you could use this relationship over here, where we have 1 calorie is equal to 4.184 joules. So we can see in this relationship that the calorie is a larger unit of energy than the joule because there's more than 1 joule in 1 calorie. Closely related to the calorie is the nutritional calorie, and the only thing different about the nutritional calorie, at least if we're looking at the symbols, the only thing that differentiates the symbols of regular old calories and nutritional calories is that in the nutritional calorie, the C is capitalized, so it's capital C-A-L. And there are 1,000 little c calories in a big C nutritional calorie. And so when you look at the nutrition facts on the back of your milk or your donuts or whatever, what you're reading it talks about all the different calories, calories from fat, total calories per serving, all that stuff. Those calories are the nutritional calories, the big C calories.
So like for example, for children they recommend either a 2,000 or 2,500 calorie diet, and they're talking about big C calories. And we're going to talk more about that when we do the calorimetry experiment with potato chips in the lab next week. You'll be figuring out the caloric content of a potato chip experimentally. So basically what Ben did is he just reviewed a lot of what we talked about. So hopefully that really ironed or cemented some concepts for you. And again, the total energy is the sum of the kinetic and the potential energy. And we'll be talking about the nutritional energy unit, the calorie, in the laboratory next week. So energy is the capacity to do work or transfer heat. Heat is the quantity of thermal energy that gets transferred from one object to another due to a change in temperature, and again, measured in joules. Some people will define heat as the total random kinetic energy, total. What you'll see is that heat always flows from the warm object to the cold one. So for example, if you went skiing over spring break, let's say after you went skiing, your hands were really cold, you come back to the lodge or back to wherever you're staying, and you want some hot chocolate to warm your hands, you'll put your very cold hands around the mug of the hot chocolate, and heat will transfer from the mug to your cold hands. We used to do a lot of sleigh riding up north when it snowed, especially on snow days. So we would go down the hill a few hundred times, we would come back in, and we would take off our socks and we would just put our feet under our dog because her warm heat warmed our very cold toes. Or you could put them by the fire, but it was more fun to put under the dog because she liked it and she was furry.
Don't let you put your tongue on a pole.
Don't
Cold
put
pole.
your tongue on a pole, it'll get stuck there.
That's such a good movie.
That's silly. What stupid movie is that?
The Christmas
It's like,
Story.
what movie is that?
A Christmas Story.
Oh, didn't see that
He
one.
sticks his tongue in it. Oh, yeah. I watch it like every year. I watch it every year.
All right, what you will also see is that any heat lost by a substance must be gained by another substance, and we'll talk about that in more detail next time. Now, heat energy happens to be disorderly atomic motion, whereas other forms of energy are orderly. But entropy is a measure of the total disorder in a substance or a system, and we'll talk about entropy in a lot more detail toward the end of the chapter. But natural reactions favor disorder. Disorder is actually a good thing, and that helps drive thermodynamic favorability. For example, over the weekend, I'm sure you were told at least a dozen times to clean your room. I told my daughter at least 10 times, clean up that pigsty. So she knows she's not getting ice cream Sunday night if that room isn't at least passable. So she finally cleans up her room on Sunday. I go in there yesterday and I'm thinking, why did she even bother? Because in 2 days it looks like a tornado went through there. Now I'm not teaching her about entropy yet because I'll get something fresh back. But natural processes favor disorder. If you have a deck of cards, all the cards are numerical, all by the same suit. You shuffle the deck, you have disorder. Up north, very pretty during the summer, all the flowers on the tree. Autumn hits, all of a sudden the amount of day length decreases, it gets colder, the leaves change color, they fall off the tree. Disorder. Right now we have order in the classroom. Everybody's sitting there. Some of you are counting the minutes so you can get out of here to go to lunch, but there's order. As soon as the bell rings, total disorder. All right? So natural processes favor disorder. Michael, when that falls on you, make sure you don't get hurt, because I don't want to write the accident report, and I don't want you hurt. All right. Energy, capacity to do work or transfer heat. Heat is the quantity of thermal energy. Temperature is a measure of the average random kinetic energy. We're talking about the intensity of the thermal energy that particles have. What you will see as you increase temperature, particles move faster, their average kinetic energy will increase as well. Temperature, typically measured in Kelvin on the international system. The only thing you will do in degrees Celsius in this chapter is calculate the change in temperature, and I'll show you why in a few minutes. What you want to be able to calculate is heat transfer, abbreviated with a Q. How much heat gets transferred depends on 3 factors. The specific heat. That's the quantity of heat that gets absorbed to raise 1 gram of a substance 1 degree Celsius. Your unit will be joules per gram degree Celsius. And each substance has a unique specific heat. and you will find these on the back of your periodic table. We will be using the remainder of the tables on the back. So table 3 is right here. You have different substances and their specific heats. Which substance has the greatest specific heat? Water. Then air.
No, it's
No, you're right. Then paraffin. Cool.
and then alcohol.
No. That's, oh yeah, 2, right. So first, second, third, fourth. All right. Which substance has the lowest specific heat? They're really close, but lead wins. All right. So each substance has a unique specific heat. The unit is joules per gram degree Celsius. Now you may want to write a lowercase c by specific heat because that will be the letter to represent specific heat. So 3 factors help determine how much heat is transferred. One is specific heat. That's the quantity of heat that is absorbed to raise 1 gram of a substance 1 degree Celsius. So if you have 1 gram of water and you want to raise it 1 degree Celsius, the specific heat of water is 4.18 joules per gram degree Celsius. A second factor is mass, and this you will like. Mass is abbreviated with an M, unit grams, and you don't have to convert to moles. All right? The other factor is the change in temperature, abbreviated delta T. We typically leave this in degrees Celsius, and I'll show you why. The change in temperature is the final temperature, abbreviated TF, minus the initial temperature, abbreviated TI. So if you have a substance with an initial temperature of 30 degrees Celsius and you heat it and its final temperature is 70 degrees Celsius, what is its delta T? 40 degrees Celsius. Maintain that 1 decimal place. If you were to do it in Kelvin, then the TI would be 303.15 Kelvin, and the TF would be 343.15 Kelvin. So what's delta T? 40 Kelvin. So these are actually equal. So for delta T, you can just do it in degrees Celsius, making life much easier. And the way you calculate heat transfer Q is you multiply the mass, which will be given, the specific heat, which you will get on the back of the periodic table in table 3 once you know the substances, and delta T. So Q, heat transfer, in joules is equal to MC delta T. And you can take a look at these units. You've got grams, you've got joules over grams degrees Celsius, you've got degrees Celsius. So these will cancel, and Q will be measured in joules, capital J for joules. Easy peasy? Let's do the first 3 examples. Now, you can calculate Q, or you could calculate M, you could calculate C and figure out what the substance is, you could calculate delta T. You also could calculate TI or TF, so we'll do all variations here. The first problem says how much energy, that's Q, or it might say how much heat is transferred, is required to heat an iron nail with a mass of 7 grams from 25 degrees Celsius until it becomes red hot at 750 degrees Celsius. So let's get the information down. We want to know how much energy. The mass is 7 grams. The initial temperature is 25 degrees Celsius. The final temperature is 750 degrees Celsius. And we need the specific heat for iron. What's the specific heat for iron? 0.448 joules over gram degrees Celsius. What's my delta T? We just do the final minus the initial. So Q is equal to MC delta T. We've got 7 grams. We've got 0.448 joules over gram degrees Celsius. And we've got 725 degrees Celsius. So we have 7 times 0.448 times 725. And keep track of the sig figs. We'll hit this in a sec. This is what pops out of the calculator. Again, grams cancel, degrees Celsius cancel. 2 sig figs here, so 2,300 joules, or 2.3 times 10 to the third joules. Easy peasy? Yes? No? Anybody with a pulse?
Anybody with no pulse?
Anybody with a pulse? Q, heat transfer.
We're done?
No, but it was a good try. We're almost done. Number 2 is a little more challenging, but we are very smart children, so we can do this. Number 2 says if 4,582 joules of energy, that's my Q, are added to a 103 gram piece of copper. So my mass is 103 grams. I need the specific heat of copper. What's the specific heat of copper?
0.387.
And it's initially at 10 degrees Celsius. We want to know the final temperature. Be very careful in these initial and final temperatures. Don't get too algebraic with it. Keep it simple. Solve for delta T first, and then do the other piece of it. So we have Q is equal to MC delta T. What is delta T equal to? No. From this equation, solve for delta T. Q divided by MC. So delta T is equal to 4,582 joules over the mass and the specific heat. So delta T in degrees Celsius, the only parentheses you need in your calculator are those big ones in purple, if that's not clear to you. Is 115 degrees Celsius. You're down to 3 sig figs at this point. Now be very careful with initial and final. I could ask for the initial, I could ask for final. We know that delta T is equal to final temperature minus the initial. If I'm solving for final, I need to add TI to both sides. So my TF then is my delta T plus my initial, and that's 125 degrees Celsius. But if you solve for TI, it's a little different, and I tried to give you all variations on your classwork. Make sure you're comfortable with that type of question. Definitely going to see it on your next quiz. Is that one clear? Piece of cake? So if you're asked for the final or initial, solve for delta T first, then do the second piece of it. It'll make life a little bit easier. Make sure your answer makes sense at the end. The final minus the initial must be equal to the delta. Why don't you try number 3? I'll help pull the variables out with you. Number 3 says if 60.3 joules, so that's Q, actually it says 60.03 joules, are added to a 50-gram piece of lead, so the mass is 50 grams. The specific heat of lead is what? That's the littlest one. Until a final temperature of 100 degrees Celsius is attained. We want to know the initial. How are you going to go about solving that? Huh? What are you going to solve for first? Go for it. What'd you get? I got this. Okay. Did you get this? Piece of cake? Cool. On your classwork, you guys will be nice and ahead. No homework for you. You want to do, on your classwork, you want to do the puzzle. Well, there are some basic terms like energy. If there's any term you're not clear with yet, just don't do that one yet. We'll hit it tomorrow. But you also can do numbers 1 through 3 on the Q is equal to MC delta T like we talked about today. So I'll get that out to you now. Everybody's here. That'll make it easy. The puzzle's very, very little, so you have to write small. But hopefully you have a better understanding of some key terms with thermodynamics, such as energy, potential energy, heat, heat transfer, first law of thermodynamics. You already got it, Michael? Questions? No questions? You're good? All right, right now your quiz is slated for Tuesday. You actually will be more than ready on Monday, but we'll decide as the week goes on when you want to do everything.